Earth composition and plate tectonic theory. This marks a little bit of a shift in our course. First, from our first module where we discussed a number of preliminary things, into our main first unit where we're talking about physical geography, and into the first module of the first unit where we look at the actual building up of mountains. This is the first of a number of lectures where we're going to be doing that. Here we're going to explore some preliminaries as we look at the composition of the Earth and how it gives rise to the theory of plate tectonics. Several goals for this lecture. In general, we want to explain some of the locations and processes responsible for topographic reliefs on the Earth's surface. To do that, we'll sketch out the structure of the Earth as a foundation, quite literally, for the theory of plate tectonics, and some of the forces, both convergent, pushing together, and divergent, spreading apart, that result from the interactions between tectonic plates. Towards the end of Module 1, we built up a definition of mountains that gave us a map looking like this, showing us some of the different mountains around the world. And as you'll recall, we've defined these mountains on the basis of a number of different criteria. Some mountains are mountains simply because of their elevation. Others, even if they're at lower elevation, are deemed mountains because of their slope or their relief. So that leaves us to ask the question, what's responsible for this difference in elevation that we see around the world? Why are some parts of the world higher and other parts lower? And that's what we're going to tackle during this module. A little bit of a sketch of what we'll be doing over the course of our first unit. We're actually going to take a little bit of a wandering tour through the physical geography of mountains, starting in this module with looking at how mountains are built up, but going on to think about mountain climate, and ultimately how mountains are broken down and eroded into the landforms that we see. So if we're going to start with the question of where mountains come from, we actually need to know a fair bit about the Earth, or at least a few key points about the Earth. One thing to note here is that we're taking a pretty cursory glance over a very, very complex subject. So if geologists are listening to this, my apologies. We're simplifying things down greatly. We're talking about, in the space of a few lectures, what some people spend their entire lives studying. But nonetheless, we can take away a few key points. One of these is that if we're looking at the Earth, we actually need to get some idea of how the Earth is formed. What's inside, deep down beneath the planet that we know the surface of. One thing we can take from this is that Earth is actually both quite old and quite complex. The Earth formed about 4.6 billion years ago as the gas and the masses that made up the Sun and the rest of our solar system started to coalesce due to gravity and to solidify. So the Earth is actually made of a lot of the same materials that go into the other planets of the solar system. It also creates a structure that's somewhat sorted by density. And we'll take a look at some of the layers that you see in the image at right as we move onwards. At the same time, it's a little bit of a trip thinking about the actual size of the Earth. We've not actually been down into the center of the Earth as much as Jules Verne or the science fiction movies based on his work might imagine fantastic wonders deep down underground. The deepest humans have actually drilled is only about 40,000 feet. That was a Soviet project called the Kola Super Deep Borehole. As XKCD put it, it was a Soviet project to try to drill through the Earth's crust to the mantle just to see what would happen. Russians are awesome. But here's one way to start to put this into perspective. The radius of the Earth is approximately equal to the distance from Anchorage to Miami. The areas that we really know particularly well would only get us between, for instance, about Miami to Orlando. That's where all of the geological work that's been done on evaluating mountain structures is. That's where we've gone looking for ores, looking for oil. But the Earth goes down a much longer distance. So how do we know about what's actually in the Earth's interior? Most of our knowledge comes not from direct observation, we can't actually go down there, but from rigorous inference. We can look at the content of the Sun and other planets in the solar system, as well as our knowledge of the processes that make them, and get an idea of what elements compose our planet. We can make some inferences based on the mass and density of the Earth. We know based on the behavior of Earth's orbit what its mass is. And lastly, we can actually understand a lot based on the fact that Earth has a magnetic field. It has a charged north and south pole that doesn't exactly line up with the geographic north and south pole, and in fact it fluctuates over time. And that suggests that in some part of our planet there's some fluid motion going on. We'll see a little bit more of how that works a little bit later. Another key piece of information deals with how seismic waves travel. When earthquakes take place, or North Korean nuclear explosions, we actually see them generating waves of force that propagate through the Earth. Some of these waves propagate differently than others. So, for instance, here we see that there are P waves that can move through liquids and S waves which can't. And so based on where these different waves propagate and the speed at which they propagate, we can actually get some sense of the different layers as we get down to the Earth's core. So here's a schematic of what we're looking at when we look at the layers of the Earth. And it's important to note that we can do this in a couple of different ways. We can look at the physical characteristics of these layers based on how they respond to stress, particularly in the form of seismic waves. And based on that, we could look at the core of the Earth, both a solid inner core and a molten outer core. We could look at a solid mesosphere, and then near the surface, a lithosphere and an asthenosphere. Those last two are pretty important. We'll talk about them a few slides down. Alternatively, we could look at the Earth in terms of its chemical components. An inner core largely made of iron, a mantle made of peridotite, and a crust that's more granite and andesite and basalt and rocks that we might recognize. So this is showing this in a spherical view, as though you cut the Earth in half. We could generalize this out and look at it in a more side-by-side view if it helps to make this comparison. So you'll notice that in terms of chemical properties, we still have crust and mantle and core, but we also see physical properties that don't quite neatly line up with those divisions. Let's talk a little bit about some of these chemical layers to start out with. Pardon me, I've got a little bit of a cold as I'm recording this. Hopefully you can hear me okay. If we look at the core is the central part of the Earth. It's extremely dense, largely due to the high pressure and high temperature, made mostly of iron and nickel, and about 3,500 kilometers thick. The core we can actually subdivide into two distinct parts. There's an inner core, which we believe to be solid iron due to the high pressures involved, and a liquid outer core, largely of molten iron. And it's in this outer core that we actually see some fluid movement, or we hypothesize some fluid movement that's responsible for the changing of Earth's magnetic field. You can actually see the images at the bottom are some computer models of how some of that fluid movement might take place as Earth's magnetic field reverses periodically. Going somewhat outward, we could look at the mantle. And the mantle is solid, and it's intermediate density, largely compounds of iron and magnesium and silica. The mantle is about 2,900 kilometers thick, but because it's further out, the mantle actually comprises about 80% of the Earth's volume. And one important thing to note about the mantle is that it's plastic, or at least a portion of it is. You can think of it as being solid but still able to deform under higher pressures. There's actually a pretty important distinction between two different parts of the mantle, known as the Mohorovicic discontinuity. This from, I believe, a Yugoslav scientist who came up with this. Most geologists will call it the MOHO. And that's looking at the boundary between a solid crust and a plastic mantle. It turns out that seismic waves will actually propagate more quickly through the plastic mantle than through the solid crust. That's one way that we have observed that part of Earth's composition. And lastly, we can consider the crust. The crust is the part of the Earth that we know pretty well. It's where we live. It has rocks that we're used to seeing. But relative to the Earth's diameter as a whole, the crust is relatively thinner than an eggshell. It's pretty amazing just how small a portion of the mass of the Earth is actually area that we can see and experience and live on. Nonetheless, we can draw some distinctions too as we look more closely at the crust. And one distinction that I really want you to understand is between continental and oceanic crust. Number of distinctions both in terms of their chemical composition. The continental crust is heavy in feldspar and silica. We'll describe it as felsic. Oceanic crusts are more concentrated in magnesium and iron. We describe them as mafic. You can think about this, if you know your rocks, as the difference between a granite and a basalt. Continental crusts have relatively low density, whereas oceanic crusts are denser. Continental crusts tend to be lighter colored, whereas oceanic crusts are darker. And here's where we actually start seeing a story starting to emerge. We can think of continental crusts as being relatively thick and relatively old, whereas oceanic crusts are relatively thin and relatively young. So here's a little bit more of a demonstration of the differences between these. If we look at density, continental crusts are a little bit less dense than oceanic crusts, 2.7 grams per cubic centimeter as opposed to 2.9 grams per cubic centimeter. This contrasts with the mantle, which is a bit denser at 3.3 grams per cubic centimeter. So we can actually think about the crust, both continental and oceanic, floating on top of the mantle. Continental crust also has varying thickness, as you can see in the map at right. In some areas, we see that the crust is very, very thick indeed, as much as 70 kilometers in the Himalayas, whereas oceanic crust tends to be very thin, 10 kilometers thick or less. You can actually spend some time looking at this and you'll see some pretty interesting patterns. Especially a lot of the mountainous regions of the world also correspond to thicker crusts. If we shift to physical properties, here's where it's really useful to not just look at crust, mantle, and core, but to explore a little bit the difference between lithosphere and asthenosphere. And you'll notice that the lithosphere and the asthenosphere don't entirely line up with that distinction between crust and mantle that we've talked about. In fact, the lithosphere contains the crust and a small portion of the upper mantle. The asthenosphere is the plastic layer, and that's a little bit further down in the mantle. So what can we say about these two? Well, I've outlined some of this already, but the key distinction is that the lithosphere is the crust and the uppermost layer of the mantle. It tends to be rigid, whereas the asthenosphere is a little bit lower down in the mantle, doesn't contain any crust, and that's plastic and more ductile. And this is really where we see the rise of plate tectonics. Under plate tectonic theory, we actually have portions of the lithosphere, relatively solid, moving around on top of more ductile parts of the asthenosphere. And that gives us a view of the world that looks something like this, in which the Earth's crust is composed of about 15 major and minor tectonic plates that are in constant motion. They don't move particularly quickly, perhaps 10 to 160 millimeters a year. I've heard this described as moving at about the same speed as your fingernails might grow. So we don't necessarily see them moving. If you were to look at your fingernails, you wouldn't actually be able to observe them growing, but over time you can see the total movement is actually something that happens. We also see that at the boundaries of the plates is where geographic things tend to, geologically interesting things, like mountain formation and volcanism and earthquakes tend to happen. And one thing that I really want to stress to you is that this is a model. This is a generally agreed upon view of the major plates that we're looking at. but the exact boundaries, the exact compositions, and particularly the history of these plates are still debated. Reality is always, always, always more complex than the models. But if we take a look at a map of interesting geologic phenomena, we can see that these look pretty similar. A whole lot of the earthquakes and volcanic eruptions are taking place near the plate boundaries on the map that we saw before. So let's think about what's going on and how this theory of plate tectonics came to be and how it can explain things. The idea that continents match up is actually an older idea than we might think about. As early as the 1500s, people started to look at some of the shapes of the continents and almost saw them like a jigsaw puzzle, particularly the notion that South America and Africa almost looked like they would fit together. That was a curiosity for quite a while, but this started to get developed into a theory by a geologist named Alfred Wegener, and he started to amass some evidence that there was, in fact, historically or prehistorically, a supercontinent in which all of the land masses might have fit together. There's one slight problem with Wegener's theory. He called it continental drift, and he didn't really have a mechanism to explain why we were seeing what we were seeing. He had an idea that there was something about gravitational force, that continents would plow through the oceans. As we've already seen, continental crust is less dense than oceanic crust, so that doesn't really work out, and this idea was rejected for quite a while. Even so, there's some pretty interesting evidence to support this idea that the continents were once united. If you look at different continents, you'll often see closely related fossils, suggesting that the same plants and animals once inhabited areas that were once together and are now diverged. Likewise, we see some paleoclimatological evidence suggesting that the continents haven't always been in the same places. For instance, seeing the effects of past glaciation in areas that are now tropical. Seeing coal that had formed in originally tropical environments in areas that are now closer to the poles, where current climates wouldn't support them. It was only really after the Second World War, though, that we got a deeper look at what's going on under the seas. Surveys using sonar actually revealed that the seafloor has a pretty complex topography in it, most particularly the presence of mid-oceanic ridges in most of our major oceans. And that suggested that maybe there's something going on down at the junctions of these oceanic plates, or what we now realize are oceanic plates. Looking more closely at these, we in fact saw that there were repeated structures in the magnetic field patterns in some of these oceanic rocks, suggesting that oceanic crust wasn't uniform in age, and in fact that there was seafloor spreading taking place along these mid-ocean ridges, as new lithosphere is actually being formed. This actually gets put together and summed up by a geologist named Harry Hess, who finally comes up with a mechanism that explains some of the stuff that Wegener was talking about. The notion that that at these mid-ocean ridges, tectonic plates are moving apart, forming new oceanic crust. At the margins of the oceans, these oceanic plates are being subducted. They're being pushed down and underneath the continents, back down into the mantle, where they're melted down and recycled, almost like a giant conveyor belt. Here's another way of looking at this. In fact, we can actually think of this as being driven by some convection currents in the mantle, almost like what you would see if you were to put a beaker of water on top of a Bunsen burner, a plume of heat coming up in the center, and convection cells forming all around the outsides. So plumes of new mantle coming up underneath these mid-ocean ridges and causing convection cells elsewhere in the mantle. This theory is actually confirmed as we discover some of these geothermal vents along some of the spreading centers of the mid-ocean ridges. Some of these actually being pretty fascinating, these black smokers shooting out chemical soup into the depths of the oceans and supporting their own life systems in some of these areas. So the modern theory of plate tectonics is really driven by two key processes. We've looked at them already, but it's worth spending some time to identify them. First, seafloor spreading, as new crust is forming and oceanic crust is being pulled apart, causing divergent forces. Second, subduction, as plates collide, seeing convergent forces, pushing plates together. And as the plates collide, the denser plate, typically an oceanic plate, sinks down. So that gives us a view of the Earth that looks something like this. Seeing a mixture of different plates, some large, some small. It's worth noting that these plates often will contain both continental and oceanic crust. So if we were to look in the middle of the North Atlantic, for instance, we would see that the Eurasian plate and the North American plate are pulling apart. Elsewhere we can see areas of subduction, marked by these lines with arrows pointing off of them, indicating typically where oceanic plates are being subducted under continental plates. And this also helping us to get some sense of how of the Earth's history, of how previous supercontinents broke up and moved around to create the Earth that we see today. And this is only the most recent example of that. So we can really look at this and see plate tectonics as something of a geological Rosetta Stone. It gives us a way to reconcile some of the convergent and divergent forces that we see leading to mountain building. This also gives us a little bit of a glimpse into the history of the Earth, seeing how the same forces that are present today were also present in the past. But it leaves us with one pretty big question, and that is how do plate interactions and the forces behind them shape mountains? We'll look at that in the next lecture. Thank you.